Hello! No collection of derivative rules would be complete without the chain rule. So in this video, I'm going to explain what that is and how it works. But first, a warm-up example. What's the derivative of y equals sine x minus 3x squared plus x? In other words, for that function, if that's y, what is y prime? Answer: y prime equals cosine x minus 6x plus 1. You have the derivative of sine x, which is cosine x, minus 3 times the derivative of x to the 2 power, so you get 3 times 2 times x to the first power, there's your 6x, plus the derivative of x by itself is 1. Now I could have also written dy dx equals cosine x minus 6x plus 1. Those are two commonly used notations for the derivative. So for the derivative of y, we could write it as y prime, or we could write it as dy dx, which means the derivative of y with respect to x. Now, if I had written y equal to sine of t minus 3t squared plus t, so essentially the same function, but this time I'm using the letter t as the independent variable that y is a function of. So the derivative would be y prime equals cosine t minus 6t plus 1. Or in this case, I would call it dy dt. And I could have started with the function x equals sine of t minus 3t squared plus t. So this time we've got x as the dependent variable depending on t. X is a function of t, so the derivative x prime would be cosine t minus 6t plus 1. Or I could say dx dt, the derivative of x with respect to t, equals cosine t minus 6t plus 1. Now you might be thinking, we just took the derivative of x and we got cosine t minus 6t plus 1, but shouldn't the derivative of x just be 1? I mean, didn't I even say that up here? For the derivative of x by itself, you just get 1. Well, here we found the derivative of x, and we didn't just get 1. We got cosine t minus 6t plus 1. The distinction is the derivative of x with respect to x is 1. So if you're differentiating with respect to the variable x, you do just get 1. But in this case, x was a function of the variable t. And so when we were finding the derivative of x, we were finding the derivative with respect to t. And if there's any confusion about that, that's where the d notation comes in handy. That's why it might be an advantage to use the dx dt or d whatever notation instead of just the prime notation. Okay, next question. What's the derivative of y equals u squared? So if y is equal to u squared, what's the derivative of that? What's y prime? Well, y prime would be 2u. The derivative of u to the 2 power should be 2 times u to the 1 power, or just 2u. But what if I told you that u stands for x to the 5th power? We can do things like that in math. We can use a letter to stand for something else, some other number or expression or whatever, and then whatever's true of that letter is true of the thing that it stands for. So if x really stands for, or if u really stands for x to the 5th power, then y, being u squared, should be x to the 5th squared, which is x to the 10th. X times x times x times another x times x times x times x times x. But in that case, the derivative, y prime, would be 10x to the 9th. But earlier we said the derivative was 2u, and since u is x to the 5th, that would make it 2x to the 5th. So which is it? Is the derivative 10x to the 9th, or is it 2x to the 5th? Well, here the confusion comes from do we mean the derivative with respect to u or the derivative with respect to x? If we just write it as y prime, it's not clear. When we said y prime equals 2u, that was the derivative of y with respect to u. So we can say dy du equals 2u, or since u stands for x to the fifth, that would make it 2x to the fifth. But if y equals x to the 10th, that means that dy dx, the derivative of y with respect to x, would be 10x to the 9th. So one of those is the derivative of y with respect to u, and the other one is the derivative of y with respect to x. Now, since u is equal to x to the fifth, the derivative of u with respect to x, du dx, would be 5x to the fourth. Now, what if we multiply those together? Take dy du, which is 2x to the fifth, times du dx, which is 5x to the fourth. That's equal to 10x to the 9th, which is what dy dx is. So dy dx is equal to dy du times du dx. And this fact is what is known as the chain rule, that the derivative of y with respect to the variable x is equal to the derivative of y with respect to u times the derivative of u with respect to x. Let me show you another example. Suppose y is the function sine of x squared plus 1. Now, if you look up our derivative rules that we've already seen, if you've been watching my other videos on derivative rules, one rule we have is that the derivative of sine x equals cosine x. The derivative with respect to x of the sine of x would be the cosine of x. Now here we have the sine, but it's not the sine of just x, it's the sine of something a little more complicated, x squared plus 1. Now what if we let u stand for that x squared plus 1, so that we can write this as just sine of u, and we have hidden the complicated part. So now y is just the sine of u, and the derivative would be the cosine of u. That would be the derivative of y with respect to the variable u. So the derivative of y with respect to u is the cosine of u, and since u stands for x squared plus 1, that means it's the cosine of x squared plus 1. But du dx, the derivative of u with respect to x, well, u is x squared plus 1, so the derivative of that with respect to x would be 2x. So the derivative of y with respect to x, which is what we really want for the derivative of this function, we started out with y being this function of x, and we want its derivative with respect to that variable x. The derivative of y with respect to x should equal the derivative of y with respect to u, cosine of x squared plus 1, times the derivative of u with respect to x, 2x. So that altogether is the derivative. That's y prime, or dy dx. It's the cosine of x squared plus 1 times 2x. Or it might be better to write that as 2x times the cosine of x squared plus 1 to make it completely obvious that the 2x is not part of what we're taking the cosine of. So now that we've seen it in action, let me officially introduce, here is the chain rule. Suppose y is a differentiable function of u, which is a differentiable function of x. So you've got a composite function going on here. Y depends on something, u, which in turn depends on something else, x. Then the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. And there are other ways we could write this. We could think of our composite function, our function that depends on something which depends on something else, as f of g of x. So then the derivative with respect to x of f of g of x would be f prime of g of x times g prime of x. That is, the derivative of f of u is f prime of u times u prime. So what this really means is that the chain rule, well, it isn't really something that you use all by itself. It's like an attachment or an add-on to the derivatives that you already have. We can take each of these derivative rules that we already know and merge them with the chain rule. And now whatever the original derivative rule said about a function of x, the new derivative rule says about a function of u, but you got to multiply by the derivative of u. So for example, we already knew that the derivative of x to the n equals n times x to the n minus 1. Put that together with the chain rule, and we have that the derivative of anything to the n power is n to that anything to the n minus 1 times the derivative of the anything. We already knew that the derivative of sine x was cosine x, so the derivative of sine of anything is the cosine of that thing times the derivative of that thing. The derivative of e to the x is e to the x, so the derivative of e to the something is e to the something times the derivative of the something. The derivative of tangent x is secant squared of x, so the derivative of, this should say tangent of u equals secant squared of u times the derivative of u. Now, why is this true? Why does it work this way? Well, when we write it like this, dy dx equals dy du times du dx, it looks like we're just multiplying two fractions together, dy over du times du over dx, and it looks like the du's on top and on the bottom should cancel out, leaving us with dy over dx. So it looks like that should work. The problem is that these aren't really fractions. They aren't really ratios of something called dy by itself divided by something called du or something called dx. Instead, what they really are, instead of being fractions or ratios, they are limits of fractional or ratio expressions. So what dy dx really is the limit as delta x approaches 0 of delta y over delta x. So if you let x change by a small amount, and then y, depending on x, changes by a corresponding amount, and you take the limit of the ratio of the change in y to the change in x, as that change in x approaches 0, that's how the derivative is defined, at least in standard calculus. And so dy du would be the limit of the change in y to the change in u, and du dx would be the limit of the change in u over the change in x. And so to prove that the chain rule works, you would have to prove that if you multiply those two derivatives together, those two limits of ratios, that things cancel or work out nicely so that you get something equivalent to the limit of the ratio delta y over delta x. And actually working through this and proving this rigorously gets a little tricky. There are a couple subtleties that you have to allow for, but the basic idea does involve just canceling out a common factor that appears on top and on the bottom. I mean, in the first limit, you have the change in gx on the bottom. In the second limit, you have g of x plus delta x minus g of x, which is the change in g of x on the top. And so multiplying those limits together, it looks like those ought to cancel. One of the things that makes it a little tricky is that they're limits with different things approaching 0. One of them has just delta x approaching 0, and the other one has delta g of x, or delta u approaching 0, u being something that depends on x. But as delta x approaches 0, x plus delta x would be approaching x plus 0, or just x. And because we're assuming that these functions are differentiable, g is a differentiable function, so it must be a continuous function. So as x plus delta x approaches x, g of x plus delta x is approaching g of x, and so g of x plus delta x minus g of x is approaching 0, and so it really does work out. So I'm not going to show you a rigorous proof. You can find it various places if you really care, but it does work out. It's not quite as simple as canceling out a common factor. You have to mess around with the limits and things, but it does kind of work out the same way. So now let's look at some examples of the chain rule in action. Suppose we want the derivative of the function secant of 3x. So whenever you have a function where if there were just an x in that function, you would know what to do with it. You would have a rule that applies. But instead of an x, you have something a little more complicated, like in this case, 3x. That's when you bring in the chain rule. The derivative of just plain secant of x would be tangent x times secant x. So putting that together with the chain rule, the derivative of secant of u, where u stands for any function of x, anything involving x, the derivative of secant of u would be tangent of u times secant of u times u prime. So the derivative of secant of anything is tangent of that anything times secant of that anything times the derivative of that thing. And here, of course, the derivative of 3x would be 3. So we get tangent of 3x times secant of 3x times 3, and it would be more common to put the 3 out in front, again, to make it completely clear that 3 is not part of what you're taking the secant of. It's the numerical coefficient on the whole thing. So there's our derivative, 3 times the tangent of 3x times the secant of 3x. What about if f of x equals 5x minus 9, the quantity squared? What's the derivative of that? Well, if this were just x squared, we could use that rule about x to a power, the derivative being the power times x to the power minus 1. Here it's not just x to a power, it's something to a power. And so the derivative should be the something. Well, it should be the power times the something to the power minus 1 times the derivative of the something. So here that would be the power 2 times the something, 5x minus 9, to the 2 minus 1, or 1 power, times the derivative of the something. So here the derivative of 5x minus 9 is just 5. So we got 2 times 5x minus 9, just to the first power, times 5. We can multiply together the 2 and the 5 and write it as 10 times 5x minus 9. And we could leave it like that, or we could multiply through and write it as 50x minus 90. So either one of those would be a perfectly good way of writing the derivative. Oh, and that's not the only way we could have done this. We could have multiplied this out first. Take 5x minus 9 squared, multiply it out, and then find the derivative. Or we could have thought, hey, 5x minus 9 squared, that means 5x minus 9 times another 5x minus 9. We could use the product rule on it. So there's more than one way we could have approached this. But what if the exponent, instead of being 2, had been 20? 5x minus 9 to the 20th power. It's still possible to multiply this out, but it gets a lot more messy. If you take 5x minus 9 to the 20th power and multiply it all out, you get a big, large mess with lots of terms. So here, the chain rule is definitely the easy way to go. Again, the derivative of something to a power is the power times the something to the power minus 1 times the derivative of the something. So that would be 20 times 5x minus 9 to the 19th power times 5. And we can go ahead and multiply together this 20 and this 5 and write it as 100 times 5x minus 9 to the 19th power. Now, do you see why we can't multiply through here and leave our answer as 500x minus 900 to the 19th power? Do you see why that doesn't work? It's because the 100 is not being raised to the 19th power, but the 5x minus 9 is. So the 100 cannot go inside the parentheses, because then it would be part of what's being raised to the 19th power. Okay, what about this one? F of x equals e to the x squared minus x. Now, if it were just e to the x, the derivative would be e to the x. Since it's e to the something a little more complicated, the derivative is e to that something times the derivative of the something. The chain rule always has us multiplying by the derivative of the something. So here the something is x squared minus x, and the derivative of that something is 2x minus 1. And it might look a little more natural if we put that out in front. 2x minus 1 inside parentheses, because it's the whole thing, times e to the x squared minus x. What about if f of x is the square root of the expression 8x cubed minus 6x plus 17? Now, anytime you see the square root of something, keep in mind that that would be equivalent to that thing to the 1/2 power. Taking something to the 1/2 power is equivalent to taking the square root of that thing. But thinking of it as something to the 1/2 power means we can use this power rule on it. We know that the derivative of anything to a power is the power times that thing to the original power minus 1 times the derivative of that thing. So applying that rule here, we get 1/2 times 8x cubed minus 6x plus 17 to the, and then 1/2 minus 1 would be negative 1/2, and then times the derivative of the thing inside the parentheses that we were originally raising to the 1/2 power. So the derivative of 8x cubed minus 6x plus 17 is 24x squared minus 6. Now we could write this, turn it back into a fraction. On top we would have 24x squared minus 6, and on the bottom we would have the 2, and since this is to a negative 1/2 power, it's like the square root in the denominator. So on top we have 24x squared minus 6 over 2 times the square root of 8x cubed minus 6x plus 17. Could have left it as to the 1/2 power in the denominator, but might as well go back and write it using a radical sign, since the original function was written using a radical sign. And we can simplify this a bit because everything on top can be divided by this 2 on the bottom. So that would reduce to 12x squared minus 3 over just 1 times the square root of 8x cubed minus 6x plus 17. So that's our derivative. That's f prime of x. And notice we took the derivative with respect to x of the square root of something, and we ended up with the derivative of the something over 2 times the square root of the something. If you wanted, you could take that as a separate rule that you can apply anytime you have the square root of something and you need the derivative. But I prefer just to, instead of learning one more special rule, just think of this as one instance of the power rule that says that anytime you have an expression to a power, the derivative is going to be the power times that thing to the power minus 1 times the derivative of that thing. Okay, how about this function? F of x equals 10 over x squared plus 3x plus 5 squared. Now, there is more than one way to do this. It is possible to do this using the quotient rule, but it's easier to do it by thinking of this function instead of as 10 over something squared, you could think of it as 10 times that thing to the negative 2 power. It means the same thing, but a positive 2 power in the denominator is the same as a negative 2 power. So think of this function, and at this point we're still dealing with f of x. We haven't differentiated yet. This is still just another way of writing f of x. It's 10 times x squared plus 3x plus 5 to the negative 2 power. Now, first of all, the derivative of a constant times a function is equal to the constant times the derivative of the function. So when we do take the derivative, we're going to get the constant 10 times, and now the derivative of something to a power is the power times the something to the power minus 1 times the derivative of the something. So here that would be negative 2 times x squared plus 3x plus 5 to the negative 3 power. Remember, negative 2 minus 1 is negative 3, times the derivative of x squared plus 3x plus 5, which is 2x plus 3. And we're done differentiating. If we left it like that, that would be the derivative, but we can clean it up or simplify it a bit. We can multiply together 10 times negative 2 and get negative 20. We can put the 2x plus 3 in front of the x squared plus 3x plus 5 to the negative 3 power. If you want, you can multiply through the negative 20 times the 2x plus 3 and write it as negative 40x minus 60. And instead of times something to the negative 3 power, we can put it over that thing to the positive 3 power. So that would be probably the way I would want to write the final answer, as negative 40x minus 60 over x squared plus 3x plus 5 to the third power. Now, we could have used the quotient rule. Take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the original denominator squared. But if we did it that way, part of that would involve taking the derivative of this denominator, and we'd still have to use the chain rule for that. The denominator does consist of something to a power. So when we get around to the part of the quotient rule that tells us to take the derivative of the denominator, we'd be taking the power times the something to the power minus 1 times the derivative of the something. And we would end up with something that's kind of a mess, but could be simplified down to being equivalent to this. So we could use the quotient rule on this, but it's not the easiest way. The easiest way is what I've shown here. How about this one? F of x equals the sine of the square root of x. Okay, classic case for the chain rule. It's a function of another function. It's not just the sine of x, it's not just the square root of x, it's the sine of the square root of x. So, looking at the big picture, it is the sine of something. And whenever you want the derivative of the sine of something, you're going to get the cosine of that something times the derivative of the something. So here that would be the cosine of square root of x times the derivative of square root of x. And remember, the square root of x is equivalent to x to the 1/2 power, so its derivative would be 1/2 times x to the 1/2 minus 1, or negative 1/2 power. And so we can write this as cosine of square root of x over, and then in the denominator we have a 2 times an x to the 1/2 power, or square root of x. So there's our derivative, cosine square root of x over 2 times the square root of x. And some of you might be tempted to do a little canceling here. Ooh, there's a square root of x on top and on the bottom. Can we cancel those? No, we can't. Do you understand why? Because on top, where it says cosine square root of x, the square root of x is not being multiplied by something. Instead, you're taking the cosine of the square root of x. So you can't divide out the square root of x because it's not being multiplied by something else. It is the argument of the cosine function. So on top you have the cosine of the square root of x, which we can't just divide by the square root of x. And on the bottom, we do have 2 times the square root of x. So that can't really be simplified any further. That is the answer. Cosine of square root of x over 2 times the square root of x. Now, what about this? This is also a composite function, but in the opposite order. Instead of being just the sine of x or just the square root of x, this is the square root of the sine of x. So if you pull back and look at the big picture says this is the square root of something. And whenever you have the square root of something, or something to the 1/2 power, the derivative should be 1/2 times the something to the 1/2 minus 1 times the derivative of the something. So here that would be 1/2 times sine x to the negative 1/2 times the derivative of sine x, which of course is cosine x. Or writing this as a fraction, you've got cosine x on top, and in the bottom, in the denominator, you have a 2, and you have a sine x to the 1/2 power, or the square root of sine x. So there's our derivative, cosine x over 2 times the square root of sine x. Now at this point, I am almost done with my videos about derivative rules. I think I can take care of most of the rest of them with one more video where we use, with the help of the chain rule, we can derive rules for, well, inverses of some of these functions. The inverse of sine, which is arcsine, or the inverse of tangent, which is arctangent, or the inverse of e to the u or e to the x, which would be ln of u or ln of x, things like that. So that's what we have left to cover if we're going through all the basic derivative rules.